Today we continue building the math foundation for quantum computing. In the last video we learned vectors, simple list of numbers that can describe states like 0 and 1. Now let's talk about matrices. What is a matrix? A matrix is just a grid of numbers. If a vector is a single column of numbers, then a matrix is multiple columns put side by side. You can imagine it as vector describes a state and matrices describe a transformation, something that takes a state and turns into another one. A vector is like a point, a matrix is like a machine. You put a vector into a machine and it gives you a new vector out. This is the heart of the linear algebra and the heart of quantum computing. Why do we need matrices? Because in quantum computing, we constantly change states. We start with an initial state, maybe representing classical 0 or 1, and then apply operations like rotations, flips, combinations, gates. Every one of these operations is actually a matrix. So you can think of it like vector represents what the system is and matrix represents what we do to it. So how does a matrix actually transform a vector? The rule is very simple. A matrix transforms a vector by combining the vector's value with the matrix's row. To multiply a matrix by a vector, we do the following. Take S row of the matrix, multiply it with the vector, add up the products. That gives us the new vector. If that sounds confusing, here's the simplest possible way to think about it. S row of the matrix decides what the output becomes. Row 1 decides the new top value, row 2 decides the new bottom value. It's like S row is giving instruction. Take some amount of old top value, take some amount of old bottom value, mix them, and that will be your new value. This mixing is what allows matrices to transform vectors. That's how state changes happen. Now let's go deeper into state transformation. We have vectors. Vectors describe states like bit 0 equals on 0 and bit on equals 0 on. But a vector by itself just sits there. Nothing happens until you apply something to it. That something is a matrix. Think of a matrix as a machine you feed a vector into. So matrix multiplied by vector gives a new vector and machine multiplies by state gives a new state. How exactly does a matrix transform a vector? Let's walk through the process slowly. Imagine we have a matrix with 2 rows and 2 columns. A equals AB and CD and the vector V equals XY. When you multiply A by V, here is what really happens. The first row of the matrix picks the new top value and the second row picks the new bottom value. But how do they pick it? S row takes a mix of the old vector values. For example, the first row says take A times the old x plus B times the old y. Similarly, the second row says take C times x plus D times y. This mixing is what creates the new state. Now let's see an actual concrete example. Consider a very simple 2 by 2 matrix. We call this our flip matrix, which is F equals 0 on 0. In this matrix, the row 1 says ignore the first number and take the second number, and the row 2 says ignore the second number and take the first number. So what happens if we feed in the vector on 0? The output becomes 0 on, and if we feed in 0 on, the output becomes on 0. So our flip matrix transforms state 0 to state 1 and state 1 to state 0. Now you have seen a real mathematical transformation. A matrix changed one state into another state. This is exactly what quantum gates will do later. But quantum gates follow special rules, and that brings us to our next topic. Now let's go deeper into two special type of matrices that appears everywhere in quantum computing. First one is unitary matrices. A unitary matrix is like a perfect transformation machine. What do we mean by perfect? When you feed a vector into a unitary matrix, the output vector keeps the same length as the input. No information is lost, no information is gained, the transformation is fully reversible. You can think of it like a perfect rotation of a shape. Spin it around, move it, but don't stress it, shrink it or distort it. If I rotate a square, it stays a square. That's what a unitary matrix does to vectors. It preserves their norm or length. This is very important in quantum computing Because quantum states must always stay normalized. Their length must always be exactly 1. Now let's see an example of unitary matrix. The flip matrix we saw earlier is actually an unitary matrix. If you test it, you will see norm before transformation was 1 and norm after transformation becomes 1. Other unitary matrices includes rotation. For example, R equals cos theta minus sin theta and sin theta cos theta. This rotates the vector in 2D space. Again, the vector's length does not change. Later, we will see quantum gates like the Hadamard gate, the Pauli matrices, the rotation matrices, and all of them are unitary. Now let's move on to another type, Hermitian matrices. Hermitian matrices are another special family. These are the matrices used in measurements. Measurement in quantum computing is a big topic. We will explore it properly later. But here is the basic idea. Hermitian matrices represents quantities you can observe, like energy, spin, direction, state outcomes, etc. Hermitian matrices have some characteristics, like their diagonal elements are real and they equal their own transpose, or you can say mirror version. But the intuition you need right now is simple. Unitary matrix represents an action you can perform, or you can say operations, and Hermitian matrix represents something you can measure, or you can say observables. In the classical world, you could compare these two. A unitary matrix is like pressing a button to rotate or flip something, and a Hermitian matrix is like using a measuring device to read a value. Both are important and both will show up constantly in quantum computing. Now let's review everything we learned today. A matrix is a transformation machine. You feed a vector into it and you get a new vector out. Matrix multiplication creates a new state. This is how bits, qubits and quantum systems evolve. Unitary matrices preserve length, they perform perfect reversible transformations. These will become quantum gates. Hermitian matrices represent measurable quantities. They connect to the concept of observing a quantum state. This sets the stage for quantum computing because quantum computing is built entirely on vectors, matrices, transformations and measurement. With this understanding, you are now ready to write your first matrix transformation program in the lab section. Open your Google Colab and follow the coding part. First, let's define our classical bit vectors. Let's print them to confirm. Now we will create a simple 2x2 matrix that transforms these vectors. Let's start with a very easy example, the flip matrix. The matrix will turn 0 into 1 and 1 into 0. Now let's apply it to bit 0. As expected, we can see the flip matrix transformed the bit 0 into bit 1. Similarly, let's transform the bit 1. The flip matrix transformed the bit 1 into bit 0. This proves that our matrix really is transforming the state exactly the way we designed it to. Now let's verify that this transformation does not change the norm of the vector, which is a property that the unitary matrix has. To do this, we'll use built-in numpy function np.lineals.norm. So for the bit 0, we can see that the norm before and the norm after is same. If you do the same for bit 1, you will get the exact same norm before and after. This shows that the matrix preserves length, which is an important idea in quantum operations. And that's it for the lab. We defined vectors, created a matrix, applied it, and saw how a transformation happens in practice. That's all for today's video. Make sure you subscribe the channel and share the video. See you in the next video. Until then, happy quantum computing.